So let's zoom in a little bit here, and I want to take a particular look to talk about the BGP, the route redistribution, because you have two-way route redistribution, right? So you have all the routers connect to each other via OSPF adjacencies. Okay, in this OSPF, once the OSPF adjacency is established and they get a list of routes, each router is going to get the loopback of all the other routers. Now, MPLS works by using a protocol called LDB, or Label Distribution Protocol. This protocol, what it does is it forms an adjacency with neighbors on directly connected networks, and it exchanges label tags so that other routers know what tags have been assigned locally, and it negotiates tags. Now, MPLS, let me take a step back and talk about MPLS first before we talk about label tags. MPLS is a really neat technology because what it does is it uses the innate super fast ASICs that switches have. And the way MPLS looks at a binary level, it looks very similar in format to MAC addresses, in that the same ASICs that it used to switch MAC addresses at really high speeds in one port and out another without having to take a really complicated decision-making process like layer 3 routing that takes a long time and has to be process switched, or you can actually not process switch them using Ceph and some of the later Cisco models, but still it's a decision intensive process. In switches, you know that in most unmanaged switches, there's not really a whole lot of an OS running there. It's basically just looking at MAC addresses, writing them down the table, and then when it gets another MAC address that matches it, it puts it out that port. Well, labels take a very similar format. They're different than MAC addresses, but the way in which the router processes the labels is similar enough that we can leverage the power of those ASICs. So what happens is that if you're an ISP and you have to switch or route 10 gigabits of traffic, you're going to be using, a very expensive Cisco router, something in the GSR family. You're going to be using a big Juniper MX series router, a big heavy iron, and those are really, really expensive. And really more on the Cisco side before recently, they were really behind Juniper in the ASICs game for ISPs. So the thought of having to, buy $multi-million and $100,000 routers, 100,000 plus $500,000 routers was a big cost problem, and there was a scalability problem with the speed of backbones of ISPs, right? So in order to solve this problem, they came up with multi-protocol label switching, or MPLS. And the MPLS is kind of neat because they call it a layer 2.5 protocol. If you actually look it up on Wikipedia, or if you have any Cisco documentation or Juniper documentation, or if you read the IETF docs on it, you'll see that it is a layer 2.5 protocol. And they call it that because you can run anything inside the MPLS tag. Just like Ethernet can encapsulate IP, MPLS can encapsulate TCP/IP. You can put any protocol theoretically into an MPLS tag. So they call it layer 2.5 because it's not quite layer 2, because it also gets encapsulated inside a layer 2 frame, but it's not layer 3 because it can hold layer 3 content. But it gets kind of confusing because MPLS requires routing adjacencies to be up. It requires a very robust working routing table in order to use. So for instance, the LDP protocol, which exchanges the labels, is very similar to OSPF in that it looks for a neighbor and they bind based on the highest loopback address. So you have to have a loopback address on your devices, and it has to be advertised into a routing protocol because the LDP protocol is going to check the routing table to see what it finds. So if you turn off OSPF, the MPLS adjacencies will break, the LDP adjacencies will break. So it's really confusing to a lot of people because, like, well, you said it's a layer 2 protocol, but it really seems like it's a layer 4 protocol because it's dependent on layer 3 to function, because without a routing table, it does not work. And you're right, it's a very interesting technology that kind of goes back and forth across those layers. So a lot of people have trouble with that. But basically, the steps to configuring an MPLS network is first get your routing straight, then get loopbacks on all your devices, make sure those loopbacks are advertised into your routing protocol of choice, and then you can start configuring MPLS. So MPLS, once it forms adjacencies, it looks at the routing table, and it uses those routes. It assigns tags to those routes. And so basically, instead of having to reference the routing table in the future, MPLS can just look at a packet, know where it's destined, and say, oh, it's destined. I know that to the right of me, if a packet is tagged with the label 20, that it's going to this destination. So I can just swap the packet from label 20 to label 16 because that's what I have in my local database for the next one. The next router down the line does the same thing. Well, I know that if this guy's got a tag for 16 and I know where it's going, then that's my 22 tag. So it can do that really fast at the switch level using tables, almost like MAC address tables. So it really speeds up the network. The other thing that MPLS does is it allows you to do a lot of cool things. Since you can encapsulate other protocols in it, you can do things like create VPNs, which is what this really is, what we're talking about. Most MPLS connections that people get are layer 3 VPN MPLS connections. There's also a layer 2 connection using pseudo-wire technology where MPLS can be used to basically emulate a layer 2, and you can pass VLANs across an MPLS cloud. So I can have a switch on VLAN 2 with a port in Miami and the other switch is in New York with the other port on the same VLAN, and they can talk and think they're on the same switch other than a lot of latency. So that's MPLS at a layer 2 level, emulating layer 2. And then you can also use MPLS with what they call traffic engineering tunnels, and I can encapsulate a person's traffic in a tunnel, not just an MPLS, but in an actual MPLS tunnel, and advertise those tunnels via BGP. So then I can use BGP to make very complex routing decisions and say, well, I know that I have an MPLS path that goes from Miami to Phoenix through these 7 routers, and I know that I have another path that goes from here to here using these 7 routers, and then it allows you to really segregate traffic. And the other thing that traffic engineering tunnels allow you to do is get very granular with quality of service and assign very granular tags to packets. So there's a lot you can do with MPLS in terms of the different flavors and how it's implemented. Today we're going to talk about basic MPLS VPNs at layer 3. We're not going to talk about pseudo-wire technology, which is basically VPLS, virtual private LAN service. That's a type of that's the layer 2 implementation of MPLS. And we're not going to talk about traffic engineering tunnels. That's a little bit more advanced topic, but hopefully we'll cover that in another video. And the next thing I want to talk about here is take a close-up. I'm going to zoom in a little bit and talk about what I have here. And you'll see here that we have basically a zoomed up view of what's going on inside this PE router. And you'll see that basically we're taking the routes from each company and putting them in separate VRF tables, virtual routing and forwarding tables, or VPN routing and forwarding tables, as some people call it, but it's really virtual routing and forwarding tables. And basically any routes in VRF company B can never be in the name. So these routing tables are completely segregated. They cannot see each other, and they're separate from the main routing table, which you'll see in a second when we go into the routers and take a look at the configuration and how it works. So this is how the company's routes get into the ISP. So you peer with a company. In this video, we're going to use OSPF, like I said, because that's a very common way of doing it. So you peer with the ISP. The ISP takes your routes and puts them in a specific VRF that it is created specifically for you. Once in that VRF, okay, I've got your routes in a VRF. Now, how do I get them all the way across the country to your other office? Well, the answer is BGP. And in order to get the routes into BGP, we have to redistribute them. Now, you can see that this is going to become quite cumbersome if it wasn't for VRFs. Not only that, it would be nearly impossible to manage because routes would be all over the place. You'd have to have very complex filter lists determining what routes are going where, and it would just be a nightmare. It'd be unmaintainable and unscalable. But VRFs allow us to accomplish that pretty easily. And then what we do is we basically use some of the settings when you create a VRF. There's 2 things you really need. It's a route distinguisher and a route target. A route target determines which BGP community string is going to be attached to those routes. It's what keeps these routes separate. It also determines which BGP routes are allowed to go into that table, because they also have to have the same route target in order to come in. That's listed underneath that VRF. So route target, you can put a route target as inbound and outbound. So certain route targets are allowed to come inbound, and certain route targets are allowed to go outbound. So it's very specific, and I'll show you that. And then the other thing that is important is route distinguisher, which is a way to figure out where these routes came from. So if you look at the route distinguisher, it basically says, hey, Mr. Router number 5, I'm the one who originated this route. So if there's an issue with it, it's easy to track it down. And then, of course, once these routes get into BGP here, they go across the link, and you'll see this little blue BGP adjacency here. And you'll see that on the other side, it gets into this link here, and there has to be another redistribution. So the first redistribution is from OSPF to BGP, and the second one is from BGP back. Now, you know, if you've ever played with redistribution, that it's a very dangerous process if done haphazardly.